So today we move on to chapter 22, heading into the last three chapters of the book that we're going to cover that talk about more kind of macroeconomic type issues related to monetary policy. So, yes? I don't think, no, I have it I think it's already posted, and I think it's for the day, like 2 weeks from now. But it is posted, you can jump on it. I think it should be up there. Anything else? Yeah?
Is that final going to be on my camera thing?
No, it'll be in class with the regular final. We'll talk a lot more about that when we get to it. Okay, so our first thing we look at is something called the quantity theory of money. The history on this topic is kind of interesting, I think. So there was a brilliant mathematician, economist guy named Irving Fisher, who we learned about before. Does anybody remember what we learned from Fisher? The Fisher formula, Fisher equation, Fisher formula. What was that? That's where I stick you all. Alyssa, you got it? Fisher formula. It's a good one to memorize, burn in your memories. Who's going to take a stab? Or look quickly in their old notes. Aha, that sounds good. What is it? I or?
No,
I equals IR. Something to do with inflation. Good. What do we want to? If we write it this way, what's the relationship to? You're right. There's an inflation factor. Is this a plus or a minus? Plus. Right. So a lot of times we write it the other way, bringing the inflation over here, so that the real rate of inflation is the nominal rate minus the inflation rate. Well, that's where we made that variation. Yeah, it can go both ways, depending on if it's ex post or ex ante. So what was the difference between ex post and ex ante? Before or after the fact, right? So which one's before, ex ante or ex post? Ante. Good. So ex ante, before the fact, then we're dealing with expected inflation, and so we're trying to think about what are we going to? A banker, for instance, might be charging. What should I charge today for this loan, which is I? That's what I'm going to actually charge my customers. Well, part of that is based upon what they expect inflation to be, because after inflation erodes away the purchasing power of those future dollars that your customer is going to pay you back with, you're left with a real rate of return of IR. Okay, so that, and there was a little bit more sophisticated math behind it, but this is the equation that gives us a kind of rough and dirty approximation of the relationship between those two things. All right, so that was Fisher, and then ex post, if we've actually observed the inflation rate, the banker can say, oh, what did I really get? Well, I charged 6%, and the inflation rate turned out to be 3%, and so I really earned 6 minus 3 equals 3, right? Ex post. Okay, so another thing that Fisher did was think kind of long and hard about how money works in the economy. And so he came up with the equation of exchange. The equation of exchange. And I think he did this work in the 20s. So, the equation of exchange. This is credited to Fisher. All right, so let M equal the money supply. Could be M2, could be M1, but just in general, we're going to call M the money supply. P is the price level. What's the price level again? How much things cost. How is it calculated? Average of all things. When we say level, price level. Okay, so with the CPI, the Consumer Price Index, right? That index, we look at the level of prices of a basket of goods today, and then we look at it a month later. We take those same goods and we see what's happened to prices, and we start to build a price of the basket, which is then the average level of prices of the basket, and we can start to construct that index of numbers. So the price level is a number that reflects changes in the average level of prices of the basket of goods. Finish that sentence. Relative to what? A base year. So that's one thing to keep in mind, is that we always have to have something that we're comparing it to. And ultimately with these price indices, we're comparing it to some base year. So what was it back in 1985? That's what we mean by the level. So if the level is now 220 in 2014, if the price level in 2014 is 220, what does that mean? It's the price level, right? It's, what does that mean relative to the base year? It changed how much? 220? 120? Remember that 120? What was it significant? Why do you say 120, Austin? The base year starts at 100, right? So we arbitrarily chose a base year. And so if in 1985, if the price level in 1985 was chosen to be the base year, it changed by 100. And now we can say that's 120, what? Percent dollars. It went up by $120, went up by 120%, went up by 12%, 2.2%. What was the relationship here between 2014 and 1985? I liked your 120. 120 what? There's actually multiple correct answers to that question the way I have it phrased. 120 what? What are you whispering, Sawyer? Be brave. Okay, points. Yeah, so that's why it's kind of a loaded question. So we do have 120 index points, if you will, right, of that average price of the basket. Remember, we've got a can of Campbell's soup, macaroni and cheese, and a gallon of milk, and we've tracked that thing over the whole time, and that average level of prices has gone up to 220. And now the 120, because this is 100, also could be what? Besides 120 points, or index points? 120%, right? And what is that percent reflect? What do we call that variable? Percentage change in the price level is a little louder, a little bit louder now, a little bit louder now. Inflation, yes, you're whispering it. Be proud, inflation. So inflation is the percentage change in the price level from whatever year. This was a huge time period from 1985 to 2014, but we're just saying over that time period, prices have climbed 120%. If we do kind of a naive average of that, and we take our 120%, and then I guess let me slow down again here. The 220, how do we find a percentage change in a variable? New number minus the old number divided by the old number. And that's what makes this one kind of easy when we compare it to the base year, is we've got 220 minus 100 divided by 100, all collapses down to 120%. How many years are between 1985 and 2014? Ooh, I'm really pushing you this morning here at 8. How many? 29. Okay. So if we take, on average, we have 120% inflation over this 29-year period, what was the average per year? Who's got a calculator handy? How much? 4.14. Okay, now that was the accumulation in reality of maybe some very high inflationary times. In fact, 1985, we might have been right at that 15% per year, right? And then at other times it dropped down to 2%. So over time, the inflation rate might have climbed, but we just kind of took a simple average here and said, hey, over 29 years, that's about 4% a year. Okay, so that is our price level compared to inflation. The reason I wanted to kind of bring that back to the memory banks is that that's part of what we'll be discussing here, is that connection with the money supply. All right, any other questions there? All right, so Y, big Y, is aggregate output. We can call it income. So this is I like to think of this as being the quantity of goods and services. So when we use the word output, you can also kind of think quantity. What is the quantity of stuff that we made during the course of the year? The quantity of things. All right. If we put these two things together, aggregate output and the price level, we get nominal GDP. So price times output, price times quantity, gives you aggregate nominal income. Nominal GDP, gross domestic product for the nation. So if we start to think about the United States as a business, which is not always a good thing to do, but so bear with me. If we start to think about the United States as a business, and they make stuff, they're kind of a production animal, right? They just put resources together and make things. This is the amount of things that they made over the course of the year, and then all of those things got eventually sold at an average of those prices. And so the gross domestic product is the dollar value of all final goods and services produced within the nation's boundaries over the course of a year, over some time frame. That also is the income earned by the factors of production that made that stuff. So when we sold the golf club, this one would not go for $100, but let's say $100 worth of golf club, then the rubber maker, the handle maker got paid, the employees got paid, the steel got paid, right? All of the factors of production that went into make this final good got paid. What did they get paid? They got paid income, just like your paycheck when you collect it when you work, right? So the dollar value of all final goods and services produced within the nation's boundaries is the sum of everybody's income. All right. So we've got nominal GDP, the value of what we produced in any given year. So let me just put a little extra starburst by this. This is the value of production. Looks like my orange is almost gone. The value of production quoted in terms of prices from that year. If this is 2014, it's the value of production in 2014. If this was 1985, it's the value of production in 1985. Okay. Questions on that at all so far? Then our last variable is the one Irving Fisher brought up and was kind of part of the brilliance, I guess, of his mind, trying to put things together in the economy, and that is velocity. V is the velocity of money. So this is the velocity of money. So these two things are going to be used kind of together. How do these four puzzle pieces fit? I want you guys to think about that, and it kind of ties in here. Here's the dollar value of all the stuff that was purchased in 2014. The dollar value of all the stuff that was purchased in 2014. So how does this puzzle piece fit together? Ultimately, we're going to have 1, 2, 3, 4 things relating to each other, and this last puzzle piece is kind of important. What's the idea of the velocity of money? How quickly it changed hands, right? So the number of times that a dollar got spent. So if we have $1 billion worth of currency of dollar bills, let's say, how many times did that go from one person to the next person to the next person and kind of facilitating those purchases? How many times did the dollar turn over, right? How many times did each dollar get spent? So this is the velocity is the average number of times, per year, the average number of times per year a dollar gets spent. The average number of times per year a dollar gets spent. All right, so we can express that by using what we've got here. If this is how much stuff was purchased, and this is how many dollars are floating around out there, if there's $1 billion, if I take this divided by the number of dollars we started with, that's going to give you this. So velocity can be thought of as the dollar value of everything that got spent divided by the quantity of dollars available to be spent. And then rearranging terms, just bringing the m over here gives us the equation of exchange. So this equation is what we call the equation of exchange. All right, so this thing is what mathematicians call an identity. Sometimes accountants use that too. With debits and credits, it's an identity. That means it's got a hold just because we defined it that way. It doesn't necessarily tell us how the world works exactly, like the underlying variables that are creating it. It's just saying, hey, there's dollars, they need to be spent, and that means they must have been spent on average this amount of times. So all we did is kind of define a relationship. And so the some observations that Fisher started to make, and then eventually we'll get to Milton Friedman making some of these as well, is what are the properties of these things in the short run and the long run? Who controls this? Try to put our agents in the economy in place here. Who controls M? The Fed, right? So the quantity of money, that's what we've been talking about these last few chapters, is the quantity of money controlled by the Fed. Who controls this? Velocity. Consumers, and maybe who else? Producers, businesses, right? So kind of the private sector, how many times those dollars are going to get spent depending on maybe some other things. All right, so we've got those things. If you are kind of averaging the highs and lows, would you expect velocity to change, to be really erratic? Like sometimes, remember it's society as a whole, so you might be a little bit more erratic, but on average, would you expect the number of times that dollars get spent to be a variable that moves all over the place? Not on average, right? Because if we think about some people are falling on hard times and they're not gonna spend their money as much, they're gonna kind of hunker down. There's somebody else, as long as it's not maybe a general decline in the economy. There's some people that are making a bunch of money, they just got a brand new commission on a real estate sale, and there's somebody else that just lost their job, right? So those kind of just tend to average out of all of those ups and downs, and so we expect that the velocity of money is fairly constant, in the short run at least. So let's just put little notes here. Velocity is fairly constant in the short run. All right. If we have what classical economist assumes, classical econ thinking. Just want to put a quick comment in here because this will start to set the stage for, yes?
So if like we graph the velocity, would that kind of follow the economy with expansion and recession?
Depending on which one we graph, M2, which we'll look at some point, but M2 is fairly constant. M1 has a little more movement to it because M1 covers currency and checking account deposits. And so as like the financial innovation of ATM machines and stuff, people put more of their money in savings and then could shift it over to currency. So M1 velocity was a lot more volatile, but M2 is pretty constant. Okay, so we're going to start to tee up some camps of economists on the way they think the economy works. So the classical economists believe that markets clear, that we are in a free market economy. We have prices that are flexible, are able to change. Both resource prices and output prices are really flexible and they adjust to their equilibrium levels. So this is one of the key assumptions here. Wages, other resource prices, and output prices are flexible. And this means that the flexibility part means that the economy stays at what we call the full employment level of output. So the economy stays at full employment. Markets clear. The economy stays at full employment. So if we look at what's going on in the economy, if prices are able to adjust, people are always able to move resources from an unproductive use to a productive use. So it allows kind of this fluidity in the marketplace. To tie this back to the principles concept of the production possibilities frontier. So if we go back to how much beer and pizza can we make? Well, we can make this much beer, this much beer, this much beer, right? And this much pizza. These are that shows us maxing out our resources. If we're on the edge of the frontier, we can't do any more. We can't have any more. If we're at point B, there's no possible way we can have more beer without sacrificing some pizza. That means we're efficient. How do we get to that point where resources are able to move to their most productive spot in the economy? We got to have, for one thing, flexible resources. Resources also sometimes need to be mobile. So we run into different constraints where that might be difficult at times. But for the most part, the classical economists thought that with prices being flexible, markets will clear, and we'll see the economy somewhere along this frontier at what we call the full employment level of real GDP. We're operating at kind of the maximum. Okay, questions or comments there? All right, so one thing that we do know, or I should say do know, but I guess all economists pretty much agree to, whether you believe in the flexibility of wages or that wages and other resource prices might be a little inflexible, which we'll cover later. All economists tend to agree that eventually we get to that full employment level, so that the economy will eventually get rid of its rigidity and make its way to that efficient level of output. So the equation of exchange in the long run, just rewriting it here, if velocity is fairly constant, I'm going to put a bar above velocity. That's our math notation for basically fixed at some level, or it's constant. And then also, at a snip of time, if we're always at this efficient level, the classical way of thinking, at any given point in time, this is the classical economists, because they're thinking this is basically the short run and the long run, because they think prices are free-flowing. What does this say about this relationship? Now we're starting to draw something based on some hypothesis. What's the connection now between money and the price level? When money goes up, price goes up. So prices are not something that's controlled by the Fed, but money is. And so if we do a 3% bump here, that's going to lead to a 3% bump here. A 10% bump here is a 10% bump here. And so that is the conclusion we draw from the long run, is a one-to-one relationship between money supply and the price level. So the conclusion here of this is now transitioning into what we call the quantity theory of money. The quantity theory of money. And that theory is, I don't know if I want to use what they exactly say it here. I'm trying to be consistent with your book the way they got it. If velocity is fairly constant in the short run, and output is at the full employment level, then changes in M, the money supply, will be proportionately matched with changes in the price level P. If velocity is fairly constant in the short run and output is at the full employment level, then changes in M will be proportionately matched with changes in P. Let's just write that little example. If the money supply is bumped up by 3%, then the percentage change in the price level, which is also inflation, will be 3% in the long run. Okay, questions so far? So, if we were to graph out, money and inflation, and this is percentage change in money supply, sorry. Percentage change in the price level, inflation, and percentage change in money growth. If we were to graph that out, what does the quantity theory of money tell us that line would look like? Well, how would you graph that? Be perfect what? Line from where? From the origin, bottom to top, how many degrees? 45. So yeah, we wouldn't want to, we're not going like this or this, or this, but a 45-degree line gives us that one-to-one prediction, right? So we've got a one-to-one prediction, and I will not draw a perfect 45-degree line that looks like that, is what we think that should look like in the long run, which is a testable hypothesis. If we gather data on the U.S. economy, let's see what it looks like. And so there's a couple graphs in this chapter, is what I was queuing up for you. So, this is the United States, the one on the left. These are all dates. 1870s, 1930s, 1920, 1950, 1990, 2000, 1960, 1900s, 1910, 1970, 1940. You can see their dates are all over the board, right? It's not a linear progression of how things have changed. They're just kind of scattered. And we just simply took how much money growth happened versus what the inflation rate was. And so that's what the data shows. So what do you think eyeballing that sucker? Yes or no?
See a decent line of best fit in there that goes that way.
Yeah, so eyeball method, I guess, here let me put the theory here. I mean, this is what I just drew on the board. So is that a good fit of those data points?
Yeah, you move it a little bit.
Move it, move it, move it.
Your intersect
Ooh.
point's lower.
Yeah, so down here, there's some sort of line that seems like we do approximately have that one-to-one relationship, but it's not starting here, right? So we got that going on here, and here's data from all over the world. This was average money growth from a larger time period, 2000 to 2010. And we've got Zambia, Ukraine, we got some places in trouble, we got the United States, Japan. Again,
Closer to the origin.
yeah, a little closer to the origin, but, and the scaling's a little bit different here. This is a -5, -4, actually not too bad. So, something like that. So we got the one-to-one, but we don't have quite the whole price and quantity business. Let me put this up. So if we go back to the equation of exchange, and we do another little math trick. See if my math people, I know I got a couple of you in here. What is the approximate relationship of percentage changes and the multiplication of two variables? I'm searing over here.
Right.
So how percentage changes in M and V, or any of these for that matter, how they can be approximated when you have the multiplication of two variables. There's a little math trick. It's pretty simple little math trick, by the way. Not to say that it's simple to remember, that you don't use it all the time in math. So I'm not trying to say you're an idiot or you're a bad math major if you don't remember this. But
That's how you really feel.
you guys know I just tell it straight up. So you can add the two together. You can add the two together. So one little thing here for percentage changes is how the percentage changes relate with each other is you can take the percentage change in M plus the percentage change in V equals the percentage change in P plus the percentage change in Y.
So the total change on one side has to equal the total change on the other
Yes.
side. And
Yep.
it doesn't have to be like the change in M doesn't have to be the same as the change in P.
Good. You said it well. Did you hear that? Corbin, say that again, because that was good. In fact, come to the board. Let me put you on the spot so you can point. I'll give you a golf club too if you want. But you said it really good. So just kind of explain that to the class. Of why that equation works.
Because it's inequality, yeah. Because it's inequality, everything that's done to this side has to be the same as what's done to this side. So if stuff on this side changes, then the same amount of change has to occur on this side. But the change in M doesn't necessarily have to be the same as the change in P. Just the total change on one end has to be the same as the total change on the other.
Make sense? So kind of the total effect. So in fact, we could have some going up or down. We could have velocity decreasing by 1%, but money supply increasing by 10%. 10 minus 1 equals 9. So this stuff changed by 9%. Junk over here had to have changed by 9% too. So that's all this thing is doing, is kind of blowing that apart. All right, so we know that this little guy is inflation.
So that saying that half of it was true, but the bottom one is true?
Which top and which bottom?
When we have all the changes,
Yeah.
true, but the one on top is
No, it's just they're both true in terms of how the math works out. But it's, this one you would have to plug in numbers, and here we can work in percentages. So if we're thinking about this equation holds in absolute, like, and we're going to do a problem here later. I don't know if we're going to have time today, but if the money supply was 10 billion, velocity was 5, 10 times 5 is 50, right? And price level is 220, and this was whatever it was, that has to hold. Now we're saying, what if velocity changed from 5 to 6? Right? What would the percentage, how would that change? How do the variables relate to each other? The math tells us that this is the relationship that has to hold. If this thing changes by 10% and this one stays constant, something over here had to change by 10%. Okay?
We know, just saying that in that example, when n changed by 3%, does that mean t had to absorb that change of 3%? Meaning y could have absorbed some of that 3%?
Yeah, that's a good, and that's exactly where I'm going with that. That's right. Yep. So up here, we kind of assume that that change was being absorbed all here, as you said. Yep. And that's what we're going to show here. So from what we've done with the assumptions we've made and maybe the observations in the real world, what is the percentage change in the velocity of money? Is that a big number or a small number? It's a small, and we assume it's small, and we observe that it's small. So that was our theory. From an equation standpoint, if this is small or close enough to 0 to call it 0, what can we do with it from our equation standpoint? Just remove it. Get rid of that sucker, right? It's like, okay, in the real world, well, heck, this is 0 anyway, so screw it. We just X it out, right? So that's through what we maybe believe in theory, and then ultimately what we tested in the real world is that velocity doesn't change very much. Now, if velocity remains pretty stable, we have our real equation that shows the relationship of this stuff. Now I'm going to bring this over to this side just so I can call it inflation. Inflation is equal to the percentage change in the price, which is just this thing all by itself. Get rid of this sucker, bring it over to this side, and I get the percentage change in the money supply minus the percentage change in output. Does that work? Does that work with this graph? Does that work with this graph better?
There's more room for it. So there's more wiggle room.
There's more wiggle room. And
Changing accurate alpha on their y, the money supply, and then 19, 18.
okay, so what is the thing that we're doing if we're trying to make this equation match these numbers, what would be a way we could test the theory, the quantity theory of money? What would we need to know to kind of get this thing the way we thought we saw it? We were up here, and now we're down here. What does this need to be, this intercept? Focus in here. If I have a line, so this equation was that one. Now it's that. you're being too, I think you're thinking too hard. How do we make this be this? We can test this if we know the long run percentage change in output, which is economic growth. If the economic growth of the United States was approximately 3% or 4%, then that would support the quantity theory of money. So that's our intercept, right? So over this 100-year period from 1870s to the 2000, I can't remember what our last date was, 2000s, if the United States experienced 3% growth, we plug it into this formula, the intercept is a -3. So this matches the data, right? I see a wrinkled brow. Make sense? So we started up here, 3% growth in the United States. The quantity theory of money is pretty solid in the long run. In the long run. All right, that's where we'll pick up next time.